Hello. So in this example, we are going to be applying the first fundamental theorem of calculus. So first fundamental theorem of calculus is almost exactly what's actually already written up here, which basically says that if we have an antiderivative of this inside, then capital F of x over there is going to be that antiderivative with the x minus that antiderivative at 0, basically. So in particular, this is telling us that if we have some antiderivative of our actual sort of, see if I can do this thing. So a little bit further there. So if we have some antiderivative of this, and let's say it's called little f of x. Well, no, that offends me as a math person because they always use capital letters for antiderivatives, which, spoiler, is why that's a capital F. So I'm going to make this a capital G of x. There we go. That makes me feel better. So if we find some antiderivative g of x of this thing up here, then that integral is actually that antiderivative at x minus that antiderivative at 0, or whatever the bottom letter is there. So strictly speaking, it turns out that really what it is we want the antiderivative without the plus c part, which is what this of 0 is going to do. So often the minus f of 0 or g of 0 isn't even written as part of it, but I'm going to show you sort of what exactly is going on as sort of a consequence of this. So I'm going to start by finding an antiderivative of this. So here, right, my little f, the integrand, the inside, is this x squared minus 3x plus 1, right? So I want the g of x, capital G of x. So I want to take the antiderivative of this, but remember that's for a polynomial, we increase the power by 1 and then divide by that new power. So here I'd increase it by 1 to get x cubed, and then divide by 3, so I get 1/3. Here I'd increase the 1 to 2, so I get x squared. The 3 is still there, but then I divide by 2, so I get 3/2. And my x, so this is really sort of like x to the 0. Not that I'd normally write that, but I can think of it as being x to the 0. So I would increase it by 1 to 1, then divide by 1, which does nothing, meaning that this just becomes x, right? So this is an antiderivative. And the whole thing, though, about the fundamental theorem of calculus is supposed to sort of link the definite integral, which is sort of what this is, right? Because it's sort of, we're used to having sort of numbers in both spots, but here we have a variable. Nonetheless, it's sort of a definite integral. And it's supposed to link that to the idea of the indefinite integral, which is this collection of all of the antiderivatives. So if I wanted to make this the indefinite integral, I'd need to add that plus c, right? Now, what happens if I then do this, right? Well, I know what g of x is now. It's 1/3 x cubed minus 3/2 x squared plus x plus c. But then the claim is I'm going to subtract g of 0. So let's see what happens when I do that. Well, g of 0, I'm going to have 1/3 0 cubed minus 3/2 0 squared plus 0 plus c. Okay, so let's simplify this a bit. 1/3 x cubed minus 3/2 x squared plus x plus c minus, sorry, again by convention this should be a capital C, and I want to make that clear because I am a stickler for details. Sort of a occupational hazard. So let's see, this is 0, right? Because 0 cubed is 0 times 1/3, still 0. Similarly, that's 0. Well, that's clearly 0. So the only thing that's left is c. well, what do I get? Well, 1/3 x cubed minus 3/2 x squared plus x plus c minus c. So those cancel whatever they are, right? Because whatever I plug in for one c, I have to plug in for both. They're the same c coming from the same origin, right? So they cancel. But what's that get me back to? Well, it gets me back to this thing, which, as you might notice, was the original sort of antiderivative I got before I made it count for all the antiderivatives, right? And this is not an accident. This is actually the sort of interesting thing that the first fundamental theorem of calculus is actually capturing, is that sort of regardless of which antiderivative you decide to choose, right, whatever you put in for c, it turns out that writing it this way, right, this weird sort of almost definite integral, it always cancels out that plus c, and as a result, it really didn't matter which antiderivative you chose because the definite integral is still going to sort of get the same result at the end. It's still going to have the same number. And so the first fundamental theorem of calculus then is sort of trying to capture this idea that, like, in some sense, when you're doing definite integration, when you're doing definite integrals as opposed to indefinite integrals, which antiderivative you choose doesn't seem to matter. And it all sort of works its way out like this did. All right. So that's that.